number discrimination without training. The studies just mentioned have all relied, to some extent, on training. While these studies do suggest sensitivity to number, evidence for spontaneous numerosity discrimination would mean that this ability is not simply the result of long laboratory experience, but something akin to what Gellistel, 1993, referred to as a mental primitive, or natural ability. That is, spontaneous use of number would suggest that it is salient to animals, not secondary to other characteristics like duration, size, or intensity. There is reason to think that this is the case. In a study by Cantlin and Brannon, 2007, rhesus monkeys were given a delayed match-to-sample task in which matches could be made based on number or on one other dimension, i.e. color, shape, or surface area. Figure 6.7. Each of the monkeys had previous experience with delayed match-to-sample tasks using photographs of scenes, but not all had previous experience in tasks that used number as a key feature. Cantlin and Brannon found that regardless of previous number experience, the monkeys primarily based their matching on number, even though they could have responded based on another dimension. Figure 6.7. Example stimuli used in Cantlin and Brannon, 2007. In the delayed match-to-sample task, rhesus monkeys primarily chose matches based on number. Okay, so for each of the setup methods, they have a standard trial and a probe trial, and they checked between number versus shape, number versus color, and number versus surface area. Okay, so for example, if you look at the number versus shape one, in the standard trial, in the sample there were 2 circles, and the choices were 2 circles or 4 squigglies. And in the probe trial, the sample had 2 circles in a different arrangement, and the choices were 2 squigglies or 4 circles. Okay, so they must have chosen the 2 squigglies, so they're matching number, they're not matching shape. That's so interesting. Human infants also show spontaneous encoding of number after seeing arrays of 8 dots over and over until habituation. 6-month-old infants dishabituated looked longer to an array of 16 dots than another array of 8 dots. However, infants of this age did not discriminate if the dot arrays differed by a smaller ratio, e.g. 8 versus 12 dots, or a 2-to-3 ratio. Similar results come from studies using non-visual stimuli. Infants will discriminate 8 from 16, but not 8 from 12 sounds. Thus, it appears that when infants are discriminating between 2 numerosities, the ratio difference is important. 1-to-2 ratios are discriminable, but 2-to-3 ratios prove difficult. In fact, the ratio difference appears to be more relevant than the absolute number difference, a feature of Weber's law. Infants will discriminate 4 from 8 sounds, even though the absolute number difference, 4, is the same as it is for a comparison they have difficulty with, 8 versus 12. Again, though, particularly with visual stimuli, it is important to consider whether infants are truly representing number or whether their behavior is primarily influenced by another magnitude dimension such as surface area. Some researchers have suggested that for infants, features such as surface area may be preferentially encoded over number, particularly for small arrays of items. Yet, similar to findings from studies with monkeys, it appears that infants will often ignore surface area and attend to number. Relatedly, in situations in which number changes but surface area remains constant, encoding surface area is difficult for infants. Together, the sometimes conflicting results, thus far, suggest that infants and animals can encode number and variables like surface area, but the priority given to one feature over another may depend on the situation. It is easy to imagine, for example, that a salient feature of food may often be its continuous extent rather than the number of individual elements, yet for objects, e.g. number of conspecifics, a salient feature may be number. Mechanisms of the approximate number system. Cognitive models of the approximate number system Posit that a real-world value is represented in the mind as an analog of that value. This analog magnitude representation is a noisy representation of the set of items, yet it is proportional to the number of items being represented. Models start to differ, however, when considering how this analog magnitude representation is formed. The information processing model, presented above to describe interval timing, can also work with number after slight modification. Meck and Church, 1983, posited that if a switch connecting a pacemaker to an accumulator could open and close for each object or event, instead of staying closed for the entire event as when timing, the contents of the accumulator would increase incrementally, ultimately resulting in an analog representation of the number. In contrast, an alternative model proposes that events or objects are detected in parallel, not incrementally as with the pacemaker accumulator, and then summed to form an analog representation. Whichever model ultimately forms the best description of the process of representing number, one idea appears uncontroversial. The performance of both human and animal participants is predicted by Weber's law. To review, for animals and humans, the sensitivity to differences between numerosities does not appear to depend on the absolute difference, e.g. that 8 and 16 differ by 8 units, but on the ratio, e.g. that 8 and 16 have a 1:2 ratio. It mathematically follows, then, that for a certain absolute difference in numerosity, discrimination is easier if the arrays are smaller, e.g. 8 versus 16 is easier than 16 versus 24, even though both comparisons differ by 8 units. This is the basis of Weber's law, and experiments across species find these hallmarks repeatedly. As noted earlier, behavior based on Weber's law also is seen in interval timing tasks. As a further example, 6-month-old infants discriminate among intervals that differ by a 1:2 ratio, but not a 2:3 ratio, over a range of durations. The absolute difference between the durations did not modulate performance. In fact, as infants develop and become better at discriminating closer ratios for numbers, e.g. 2:3 ratios, they also become better at discriminating the same ratios for duration. Thus, two magnitudes, number and timing, are seemingly processed in a similar way, showing similar behavioral signatures of Weber's law. Timing and counting also appear to show similar neural processing. The brain systems that are involved may process many types of magnitude judgments, including loudness, size, and brightness, among others. In a review of relevant literature, Cantlin et al. 2009, note that the parietal cortex, specifically the intraparietal sulcus, plays an important role in the processing of magnitude. Figure 6.8. The existing neuropsychological research with humans suggests that deficits in time, size, and number comparisons can co-occur due to parietal lesions, and in patients without lesions, functional MRI studies suggest that there is overlap in the parietal cortex for processing these magnitudes. In rhesus monkeys, the parietal cortex is also implicated in magnitude tasks. Ventral intraparietal neurons respond either to numerosity or length, but a subset respond to both. Figure 6.8, a depiction of findings across many studies implicating the parietal cortex in magnitude processing. Cantlin et al. 2009 created this figure, an inflated human cortical template, based on a review of the existing literature. Okay, so it's a brain, and the brain is labeled in these specific ways. So by the brainstem, you have the superior temporal sulcus, and then at the top of the head, you have the intraparietal sulcus, and that is where all of this processing stuff is going on, actually, on top of the intraparietal sulcus. All the brightness, number, ordinal memory, arbitrary lists, ordinal position, numbers and letters, size, and time are all kind of going on around the intraparietal sulcus. And then in front of that, you have the central sulcus, And at the front of the brain, you have the inferior frontal sulcus, and then you have the sylvian fissure between those two front sulcuses and the superior temporal sulcus, kind of in the middle. Researcher profile: Dr. Elizabeth Brannon. As an undergraduate majoring in physical anthropology at the University of Pennsylvania, Elizabeth Brannon was on the path to become a field primatologist. Through the School for Field Studies, she had studied cotton-top tamarins in their natural habitats in Panama. While working with Doctors Dorothy Cheney and Robert Seyfarth, Brannon was exposed to research approaches that blended fieldwork with the study of cognitive processes. She quickly became interested in the animal mind, and after receiving a master's degree in anthropology at Columbia University, transitioned to the field of psychology, where she earned her PhD in Dr. Herb Terrace's laboratory. During graduate school, Brannon developed new studies of primate numerical processing that have greatly enhanced the understanding of the evolutionary basis of human numerical cognition. Now, as a professor at Duke University, Brannon's work has become an example of the effectiveness of the comparative approach. She examines numerical cognition by examining its development in human infants, as well as its evolution within the primate order. To do so, she must maintain 2 laboratories, one for testing human participants and one for monkeys and lemurs. The research utilizes a range of methods including behavioral measurement and neuroscientific approaches such as functional MRI, EEG, ERP, and single-unit recording in monkeys. The comparative approach is key to Brannon's research program. By studying cognitive abilities in non-human animals and human infancy, we can understand both the evolution and the ontogeny of cognition, and thereby define the primitives upon which adult human cognition is built. More specifically, studying the approximate number system has become an ideal way for Brannon to examine cognitive processes that occur in the absence of language. Her work demonstrates how abstract numerical concepts are possible independently of language. Brannon's work also suggests that these nonverbal aspects of numerical cognition may, in turn, causally influence symbolic math abilities. The internal representation of approximate numbers and their operations provides a critical foundation for uniquely human symbolic mathematics and may indicate new interventions for math educators. The research is ongoing, but there are signs that the approximate number system is part of a system that is shared across species, and at least in humans, emerges early in development. Neuroscience and behavioral studies are beginning to shed light on whether number processing is part of a more general magnitude processing system, but there is still the possibility that some aspects of numerical ability are cognitively unique. Consider, for example, that in the laboratory tasks that form the basis of the research, participants must compare and discriminate magnitudes. Some have suggested that perhaps the shared aspects of reasoning about magnitudes occur late in the processing when these comparisons are made. Earlier, when objects and events are individuated, numerical representations may be formed within their own unique neural systems. As neuroscience techniques advance and cognitive theories are elaborated, the details of the evolutionarily primitive system or systems that allow for numerical competence will likely be elaborated. Representing small numbers. Although the approximate number system allows for adaptive processing of magnitude, it still has limitations, most notably the lack of precision in discriminating represented quantities when they differ by smaller ratios. Indeed, adherence to Weber's law is considered to be the signature property of this number system. It is all the more surprising, then, to find that in certain experimental tasks in which small quantities are presented, a different sort of limitation, or signature property, is often observed for both humans and animals. In this section, research examining the representation of small numbers will be presented, along with proposals regarding the cognitive systems that may underlie this representation. Set size signature. On the island of Cayo Santiago off the coast of Puerto Rico, a large group of free-ranging rhesus macaws have been studied for many years. The species is not native to the island, The monkeys are descendants of a group that was brought to the island from India in the 1930s for research purposes. More recently, the monkeys have been participants in studies of cognition, including spontaneous numerical discrimination. In one such experiment, a researcher approached lone monkeys and placed 2 boxes on the ground about 2 to 5 meters from the monkey. The researcher placed a different number of food items, e.g. apples, one at a time into each box, and then walked away, allowing the monkey to approach and choose one of the boxes, figure 6.10. After a box was chosen, the researcher came back, typically causing the monkey to scurry away. Figure 6.10. Test events in Barner et al. 2008 from the perspective of a rhesus monkey participant. Researcher kneels between boxes, adds 1 set of apples to a box, 1 apple at a time, adds a second set to the remaining box, 1 apple at a time, walks away from the boxes toward camera person, waits with camera person, maintaining back to subject. Given what has been previously discussed in terms of numerical discrimination, one might expect that monkeys' ability to reliably choose the box with the greater number of apples would fit Weber's law such that success would be dependent on the ratio difference. However, in this task, monkeys' behavior depended on the size of the sets. That is, they chose the box hiding the larger amount of apples when the boxes held 1 versus 2, 2 versus 3, or 2 versus 4 apples, but not when they contained 2 versus 5 or 3 versus 5. The 2 to 5 ratio, e.g. 2 versus 5 apples, should be more discriminable than 1 to 2 ratio, e.g. 2 versus 4 apples, yet the monkey succeeded in the latter and not the former. The results suggest that when discriminating between small quantities, performance is determined by the size of the arrays, the set size signature. Comparisons in which one of the sets is greater than 4 are difficult for the monkeys to make. Testing human infants on an almost identical task has yielded similar findings. 10 and 12-month-old infants crawled toward the larger quantity when comparisons were 1 versus 2 and 2 versus 3, but not when one of the sets was 4 or greater. Infants even chose randomly when the comparison was 1 versus 4. Thus again, it was the size of the sets that determined the success, though here, the infants seemed more limited than the mature monkeys and had difficulty with arrays greater than 3. The same pattern of findings was also found using a second method in which infants were timed as they searched a box for previously hidden treats. An experimenter placed items into an opaque box, though in some cases, items were surreptitiously removed before the infant began to search. In this way, one can compare, for example, an infant's search time after one object is placed and he or she retrieves it, to an instance in which 2 objects are placed, yet one has been secretly removed. Infants reliably searched longer after retrieving one object when they had observed 2 objects being placed in the box than when they had only seen 1 object placed. The longer search times occurred for arrays up to 3 items, but there was no indication from the search behavior that the infants precisely represented sets larger than 3. Outside of the primate order, other species have shown behavior that also might be indicative of a set size signature with small numbers. Euler et al. 2003, for example, found that red-backed salamanders would approach a clear tube containing 3 fruit flies over a tube containing 2 flies, but not 6 over 4 flies. Young domestic chicks similarly discriminated arrays of dots as long as sets remained 3 or fewer. In both of these cases, though, the arrays were either completely visible or partially occluded, which likely would not pose the representational demands that monkeys and infants faced on tasks in which the contents of opaque containers had to be stored in memory. In contrast to the above studies, a study with mongoose lemurs found that discrimination between small numbers was dependent on Weber's law and not a set size limit. Lemurs are prosimians, primates that split from the common ancestor to monkeys, apes, and humans, and part of the motivation for the study was to examine whether numerical sensitivity was likely present in the common ancestor of all primates. In a search time task similar to what has been used with human infants, the lemur's discrimination was determined by the ratio difference, not the absolute value. Specifically, a 1 to 2 ratio difference was discriminated even when the quantities exceeded 4, e.g. 2 versus 4 and 4 versus 8, but 2 to 3 ratios were not. Thus, in this study, the lemurs appeared to be relying on analog magnitude representations of number. The reason for the differences in results in this study and those with human infants and rhesus macaques is still under consideration. One possibility that must be ruled out pertains to the task design itself. The lemurs were tested many times, whereas the wild rhesus macaques each only received one test trial. It is possible that repeated exposure encouraged the use of analog magnitudes for the lemurs. Indeed, the mechanisms underlying the representation of small numbers and the situations in which they are deployed by an animal are the topic of current discussion.